Hey there, minions. How y'all doing? Today is Thanksgiving for us. You're probably not watching this on Thanksgiving, but I hope you have a happy day. Let's take a look at our last section. We're doing derivatives and integrals of the hyperbolic trig functions. So we have hyperbolic sine, hyperbolic cosine, hyperbolic tangents. All of them have hyperbolic versions. We take the same words that we use, the same three letters for the trig functions, just slap an H at the end to distinguish between sine and sinh, or cosine and cosh, tan and tanch. Hyperbolic sine is a combination of two functions, e to the x and negative e to the negative x, and then we average them, take 1/2. So 1/2 of e to the x minus e to the negative x. Cosh is an exact average. It's e to the x plus e to the negative x divided by 2. In fact, I'm going to show you it on Desmos so you can see how it pans out. So right here is e to the x. Right there is e to the negative x. And it wants to average those two. So when we average them, notice that like it goes to infinity really fast. So the red function, our hyperbolic cosine, tends to follow the positive sides of both of them. And if we put in cosh, it's got the exact same graph. Okay, let's go back to this. They all have different things. Hyperbolic sine looks a little bit like tangent to me. Hyperbolic tangent looks a lot like one of the inverse trig functions. Cosecant looks like 1 over x over here. Look at that. Looks a lot like 1 over x. Oh, that's not what I want. That looks a lot like 1 over x. Hyperbolic secant actually looks like the standard bell curve. It's really neat. So there are a lot of famous ones. Tanh is gone the same way as tangent is. Divide hyperbolic sine by hyperbolic cosine. There's a couple variants of it. You'll see this one a lot, but this is a version where they multiply the top and bottom by e to the x, and you get that. Now, there are famous ones in life. The Gateway Arch in St. Louis is modeled off of a trig function or a hyperbolic trig function. It looks a lot like an inverted or upside down parabola, and there are parabolas that get close to modeling it, but the exact function is this. There are other ones you see in real life, though. Golden Gate Bridge. The curve right here of the cables is called a catenary. And there's lots of versions of it like that. That's neat that it kind of cut it off like that over there. So maybe I'll put an arrow here showing that catenary. Uh, they show up in real life. There's functions in finances, stock market. Lots of fields have stuff with it. They're very niche. But we're not working with them. Your job, whatever you do, might have you working with them. So we're just gonna play around with it and see what we can learn about derivatives and integrals. The derivatives can be found easiest by using the exponential form, if you want to show what they are. So like if we take the derivative of hyperbolic cosine, we get, we're doing the derivative of 1/2 e to the x plus e to the negative x. Fun thing about derivatives of exponentials is they're not changing. Other than the chain rule here, ooh, that's missing a negative. Other than the derivative of e to the negative x having a chain rule bringing the negative down, the process hasn't changed. And so we get cosine is hyperbolic cosine, the derivative is hyperbolic sine. Now, if we had done derivative of regular cosine, we get negative sine x. But when we do the derivative of hyperbolic cosine, we get positive sine hyperbolic sine x. So they're different. They look the same though. In fact, you'll notice that all the derivatives look the same. Hyperbolic sine goes to cosine, hyperbolic cosine goes to sine. Hyperbolic tangent is still hyperbolic secant squared. Hyperbolic cotangent leads to hyperbolic cosecant squared, but it's negative. So the only real difference are where the negative signs are. In regular trig, the three that start with a C, these three had negative signs in the derivative. That's not the case here. In the hyperbolic version, just the three reciprocal functions are negative. What I mean by reciprocal is like cosecant x is 1 over sine x. That is a reciprocal. And so the hyperbolic version ones are like that. Nah, that's not what I want. Eraser, there we go. We do have another difference. The regular trig identity, cosine squared plus secant or sine squared equals 1, has a slight shift. When we do the hyperbolic version 1, the plus turns into a minus. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. The integrals are just the antiderivative, so it's like working backwards. Nothing's changed. In case you need them, the 2x functions, how do we get them? Let's look at hyperbolic sine. Let's work it out. We've got e to the 2x minus e to the negative 2x over 2. I'm going to rewrite it as e to the x squared and e to the negative x squared. This is a difference of squares, so we can factor it. And then I introduce this part right here is hyperbolic sine. And then I added in I multiplied by 2, and then I divided or multiplied by 1/2. These cancel out. But what's going to happen is the 2 comes out here, and this 1/2 gets absorbed with that to make hyperbolic cosine. So, just like sine 2x equals 2 sine x cosine x, hyperbolic sine 2x equals 2 hyperbolic sine x hyperbolic cosine x. Is cos 2x similar? One of the variants of cosine 2x is cosine squared x minus sine squared x. Let's take a look at it. Let's work through it. I've got cosine of 2x equals 1/2 e to the 2x plus e to the negative 2x. What I'm going to do, this is a tricky one to do. So I'm going to add 1 inside. I'm going to subtract 1 inside. I'm going to write 1/2 as 2 to the 4th. Not 2 to the 4th, 2 over 4. And then I'm going to take the 2 and I'm going to distribute it in and hit everything on the inside. This is a crazy. I want to get rid of all that highlighting over there, so let's do that. Then I'm going to write the 1 as e to the x times e to the negative x. We've also multiplied it by 2. X and negative x exponents, they add together, so x plus negative x is 0. E to the 0 is 1. This is still just 2. And I'm going to do the same thing over here, but with the negative 2 becoming that. This whole thing is now a perfect square, and so is this. So I'm going to take the 1, distribute the 1/4 to each set, and rewrite. This is a perfect square also. It's 1/2 squared. So we're going to have 1/2. This is the perfect square of that. This set is that one. With the 1/4, of course. And when we work it out, we see that cos 2x actually equals cos squared plus sinh squared. So it's slightly different. It doesn't have the negative sign. You know, we had a negative here, and here it's a positive, slightly different. Go back in and write this in real quick. You should remember it, but in case you don't. And that's it. We're going to do some examples with it. That'll be in the next video. Peace. Stay ornery, folks.